Hi, this is Stan Forrester for IRSC Physics, and this is Chapter 9. In the previous chapter, we dealt with rotational coordinates, rotational motion and rotational coordinates. Now we're going to talk about dynamics, what causes the motion. Just like with the transition from kinematics, or motion in a linear fashion, to forces, in other words, the causes of that linear motion. That's the transition we're making here. Okay, so last chapter was rotational motion. Chapter 9 is going to be what are the causes of that rotational motion. Okay. Now, let's talk about translational and rotational motion. Okay, translational motion, when we treat a particle as just a single object, we don't think about whether it's up or down or anything like that. We can take a look at the jumper on this trampoline. If he's just engaged in translational motion, he has upward and downward movement. He also has movement from the left to the right. All right, and he's not spinning. We can just treat him as a single particle. We'll take a look at where his center of mass is, and we just simply trace the path of that center of mass, and we're good to go. Rotational motion would be if the object, or in this case the jumper, is rotating about his center of mass, then we have an additional component of motion. Okay, most general motion is a combination of translational and rotational motion. Sometimes we can ignore the rotational motion, sometimes not. Okay, so definition of torque. When you think of torque, I would like you to think of torque as the rotational equivalent of force. All right. Now we all know what torque is. If you were to take a lever, let's take a wrench. If you were to just grab a hold of let's say a nut, you're trying to change the wheel on a bicycle, and you grab hold of the lug nut that's holding the tire there, you just try to twist that with your fingers, you're not going to have a whole lot of success. So we have what are called wrenches. That gives you a longer lever arm. You can apply a perpendicular force to that wrench, okay, and you can get more torque out of it, more twisting force. A torque is a twisting force, or a force in the rotational direction, the rotational equivalent of a force. Okay, we define it as this Greek letter tau is equal to the force times some perpendicular lever arm. Okay. Now, if we were to have any sort of general arm, there'd be like a sine theta here, the angle between the arm and the force. Okay, but that's really not beyond the scope of the course right now. Okay. Torque is positive when we tend to go in a counterclockwise direction. It would be negative if we went in a clockwise direction. Okay. Units of torque would be Newton meters, or in more traditional units, foot-pounds. Okay. Now, equilibrium. We can talk about equilibrium now because we have all the components. All right. Now, we talked about equilibrium before in terms of forces. In other words, if all the components of the x components of a force add up to 0, there's no acceleration in the x direction. Okay, your acceleration, the x component of the acceleration is 0. If we take a look at the y direction, and we're not dealing with z here, otherwise there'd be a sum over z as well. Okay, if we sum up all the force components in the y direction and they equal 0, again, the acceleration in the y direction is 0. All right, and that means that there's no acceleration in either the x or the y direction. Your acceleration is 0. But we're going to add another component here, now that we're dealing with rotational motion. The sum of the torques must also equal 0. In other words, there's no tendency for the rotational motion of the object to change. Okay, your linear acceleration means that the linear motion is going to be constant because your acceleration is 0. Your torque is 0, meaning your rotational motion is going to be 0. Okay. All right, so reasoning strategy when you're approaching one of these. Okay, you're going to select an object which the equations for equilibrium are to be applied. Okay, draw a free body diagram that shows all the external forces acting on the object. Choose a convenient set of x or y axes to resolve the forces into components that lie along these axes. Apply the equations and specify the balance of forces at equilibrium. Set your net force in the x or y directions equal to 0. Okay, again, we're dealing with equilibrium problems. Okay, select a convenient axis for rotation. Now that convenient axis for rotation, you might want to take one of the torques that's going to be really, really hard to calculate, and put your axis of rotation right there. That way you don't have to calculate it. The lever arm is 0. The distance from your axis of rotation is 0, so there is no torque there. Okay. Set the sum of torques about this axis equal to 0. Solve all the equations for any desired unknown quantities. Okay. Center of mass. Okay, we talked about this before. The center of mass is basically the balance point. If you had, say, a meter stick, and you were trying to find the balance point, you would expect the balance point to be about halfway down the meter stick, about 50 centimeters. Okay, it's a little bit weirder if you have something like, let's say, a bowling pin. The bowling pin is weighted on one side and has a narrow neck, and you'd expect the center of mass, center of gravity, to be much closer to the flared end. Okay, but for any symmetrical shape, the weight is distributed uniformly. The center of mass lies at its geometric center. Okay, that's what we're most often going to deal with in this class. Okay, so how do we find the center of mass? Okay, we talked about this before, the center of mass. Okay, but let's talk about weights. Okay, so here's a axis. We're going to choose our coordinate system so that everything is measured from the right side of the board. So we have weight 1, which is the weight of the board itself. Okay, if this is a uniform plank, then x1 is just going to be half the length of this of the board. Okay, and weight 1 is going to be applied at its center of mass. Okay, there's a weight on the end of the board, and it's all the way down here at x2. So x2, weight 2 at x2. Notice that we're going to have a lever arm here and a force. There's going to be a torque. Notice that both of these torques are going to tend to cause motion in the counterclockwise direction, so they're both positive. All right. But what about the center of mass of the whole object? Well, what we would have to do there is we would have to add up weight 1 times position 1 plus weight 2 times position 2 plus any other terms we have. Okay? And divide that by the sum of all the weights, all of the forces there. Okay? And that's going to give you the position of the center of gravity. Okay, and so we would see that the balance point for the board is right here at the halfway point. The balance point for this weight is right underneath it. But what about the two of them? The balance point is going to be much closer to the weight than it is to the right-hand side of the board. Okay. All right, so we're all familiar with force equals mass times acceleration. That's Newton's second law. So let's do a little math manipulation and see if we can't get something similar for torques. All right, first of all, we're going to take a look at the tangential acceleration. We already know that from last chapter. That's equal to the radius of motion, times the angular acceleration. Okay, so we're going to substitute then. So m equals r times angular acceleration. Now, the torque is going to be the force times that lever arm. Again, that's, in this case, that is the radius. Okay, the radius of motion. Okay, so force times radius. So it means we're going to have to multiply both sides of this by radius again. We get 1 power radius here. By multiplying both sides, we get 2 powers of radius. And so we're going to end up with the torque is equal to this quantity here, mr squared, times the angular acceleration. This quantity here, in parentheses, this is called the moment of inertia. I want you to think of this as the rotational equivalent of mass. It does have a mass in it, but it also deals with the distribution of mass. Okay, so this r squared says it's not just how much stuff is in this plane or a solid disk. Now, a solid disk is going to have the mass distributed in a very different manner than a point particle out here at the edge. Okay, and so this moment of inertia is going to be a little bit different, but this is for a single particle. And if you were to, so torque is equal to the moment of inertia times the angular acceleration, and that's pretty close. Now so force and torque, these are analogs. Mass and moment of inertia, those are analogs, and linear tangential acceleration and angular acceleration, those are analogs as well. We saw a lot of those equations in the last chapter were very similar to each other. Okay, so Newton's second law in rotational form for a rigid body about a fixed axis. Okay, so the net external torque is going to be equal to the moment of inertia times the angular acceleration. Okay, in other words, the sum over all of the torques. Okay, if we go back, let's go back here. In this case, we have two different torques here. We have a torque due to weight 1 and a torque due to weight 2. Sum of over all the torques is equal to the moment of inertia times the angular acceleration. Now, if you're just missing one of these quantities, you can do a little algebra and solve. Okay. Okay, so the definition of rotational work. Okay, just like we had a definition for work in a linear sense, we also have work for a rotational motion. Okay, we're going to define that as rotational work is equal to a torque times a displacement. Now, recall the definition of work for a linear motion. The work was equal to a force through a distance, a displacement. Okay, so again, a torque is the rotational equivalent of a force, and an angular displacement is the angular equivalent of a linear displacement. Okay, they work mathematically the same. Okay. Let's take a look at this barrel here. This barrel here is wrapped with a rope. Okay, there's a lever arm, the radius of the barrel. The rope comes off perpendicular to the barrel, so we have radius, a lever arm, times a perpendicular force. We have a torque. Now, if this barrel moves through some arc length s, that's going to be measured as some angular displacement theta. In other words, s amount of rope comes off of the barrel. It has to rotate through angle theta. Okay, and so some work is going to be done there. Okay, definition of rotational kinetic energy. Okay, just like linear kinetic energy is 1/2 mass times velocity squared, we're going to use, you can easily remember this, we're going to use our rotational equivalents. Rotational kinetic energy is 1/2 times the equivalent of mass, which is our moment of inertia, big letter I, times the angular speed squared. Angular momentum. Okay, angular momentum, remember linear momentum would be P equals mv. Okay, so our momentum equals mass times velocity. Well, here we have angular momentum is equal to your moment of inertia, your mass equivalent, times your angular speed. Okay, and your angular speed is going to be expressed in radians per second. Okay, principle conservation of angular momentum. Just like linear momentum, where we said the total quantity of linear motion in the universe is conserved. It's conserved in the x direction, y direction, z direction. The total amount of angular motion in the universe is also conserved. Okay, if you set something in motion in the clockwise direction, you have to set something in motion in the counterclockwise direction. You can't just have one without the other. So the sum of total angular motion in the universe is the same at any particular point. Okay. We have lots of different examples to run through. Please go to your exam review discussion, post specific examples, and we can work through those. All right. Have a good one.